Welcome friends. Here we discuss hyperbolic functions. The hyperbolic sine and hyperbolic cosine of a complex variable set are defined by sin h set is equal to e raised to z minus e raised to minus z by 2 and cos h set which is equal to e raised to z plus e raised to minus z by 2. Mark it as equation number 1. We note that the definition in 1 resembles to the hyperbolic sine and cosine of a real variable. Since e raised to z and e raised to minus z are entire functions, their linear combinations sin h z and cos h z are also entire function. Also, d by dz of sin h z which is equal to d by dz of, instead of sin h z we can write e raised to z minus e raised to minus z by 2 which is equal to e raised to z minus e raised to minus z divided by 2 which is equal to e raised to z minus and minus plus e raised to minus z by 2 which is our cos h z, which is equal to cos h z. Here we have cos h z is equal to e raised to z plus e raised to minus z by 2. Similarly, d by dz of cos h z is equal to sin h z. In the previous chapter, we have seen that sin z is equal to sin z is equal to e raised to I z minus e raised to minus I z by 2I, and also cos z is equal to e raised to I z plus e raised to minus I z by 2I. Now, sin z is equal to e raised to I z minus e raised to minus I z by 2y which is equal to minus I into e raised to I z minus e raised to minus I z by 2 which is equal to minus I sin h I z, that is minus I into sin h I z which is equal to sin z. Equation number 2. Putting I z in place of z in 2 and multiplying both sides by minus I, we obtain minus I sin I z minus I sin I z which is equal to sin h z. That is equation number 3. Proceeding similarly, we obtain cos h I z is equal to cos z, that is cos h I z is equal to cos z, equation number 4, and also cos I z is equal to cos h z. Equation number 5. Next we have identities involving hyperbolic sines and cosines. Identities. First one we have sin h of minus z is equal to minus sin h z. Second one, cos h of minus z is equal to cos h of minus z is equal to cos h z itself. Third one, cos h square z minus sin h square z is equal to 1. Fourth one, sin h z1 plus z2, which is equal to sin h z1 cos h z2 plus cos h z1 sin h z2. That is sin h z1 plus z2. That is just like a sin a plus b type, which is equal to sin h z1 cos h z2 plus cos h z1 sin h z2. Next we have, here we have cos h z1 plus z2. This is equal to cos h z1 cos h z2 plus sin h z1 sin h z2. This is the expansion of cos h z1 plus z2. Also, when z is equal to x plus iy, we have sin h z, sixth one, sin h z, sin h z is equal to sin hx cos y, sin hx cos hy, sorry cos y, sin hx and cos y plus I into cos hx sin y, I into cos hx sin y. That is sin z is equal to sin hx cos y plus I into cos hx sin y. Next we have the seventh identity, we have sin hz is equal to cos hx cos y. Similarly, we have cos hz is equal to cos hy, not cos hx. Here we have cos hx cos y, cos hx cos y plus I sin hx sin y. Here we have cos terms only, here we have sin terms only. Eighth one, eighth identity, modulus of sin h z whole raised to 2. That is modulus of sin h z whole square. This I can write as sin h square x, sin h square x plus sin square y. This is modulus of sin h z whole square. Next, ninth one, we have mod cos h z whole square, which is equal to sin h square x plus cos square y. Proof of all the above results follow directly from definition 1. For example, that is sin h of minus z. Sin h of minus z, we can write it is equal to e raised to minus z minus e raised to minus I, e raised to minus of, here we have e raised to minus of minus z by 2, which is equal to, which is again equal to e raised to minus z minus e raised to minus and minus become plus. So, it is e raised to z by 2, which is equal to, which I can write as e raised to z minus e raised to minus z by 2, which is equal to minus of sin h z. The above identities involving hyperbolic sines and cosines can be obtained from the trigonometric identities obtained in the previous chapter. Using the same, we prove some of the identities listed above, leaving the remaining as an exercise. First one, in the trigonometric identity, sine of minus z is equal to minus sine z. Replacing z by iz, we obtained sine of minus, that is we are replacing z by iz. So, it is sine of minus iz is equal to minus sine iz. It is equal to minus sine iz. Using 2, equation number 2 we obtained minus I into sine h of, here we have I of minus I into sine h of I of minus iz, which is equal to minus of minus I into sine h of I of iz, that is minus I sine hz. This is equal to I into sine h of minus z. Multiplying both sides by I, the above yields. That is, we have to multiply both sides by I, which implies what? Sine hz is equal, sine h of minus z, sine h of minus z, which is equal to minus sine hz. In the trigonometric identity, cos square z plus sin square z is equal to 1. That is, replacing z by iz, we obtain cos square iz, that is, we are replacing z by iz, it becomes cos square iz plus sin square iz, which is equal to 1. That is, thus we can write it as cos iz whole square plus sin iz whole square is equal to 1. Using equation 3 and 5, the above implies cos hz whole square plus I sin hz whole square equal to 1. That is, cos h square z minus sin h square z is equal to 1. Next, in the trigonometric identity, we have sin z1 plus z2 is equal to, that we all know, sin z1 cos z2 plus cos z1 sin z2. Replacing z1 by I z1 and z2 by I z2, we obtain sin I z1 plus z2 is equal to that is sin I z1 plus z2. This is equal to sin I z1 sin I z1 cos I z2 plus cos I z1 sin I z2. Using 3 and 5, the above implies I z h z1 plus z2 is equal to I sin h z1 cos h z2 plus cos h z1 I sin h z2. That is, sin h of z1 plus z2 is equal to sin h z1 cos h z2 plus cos h z1 sin h z2, our identity. According to 3 above, minus I sin I z is equal to minus I sin I z, which is equal to sin h z. Here we have brackets, which is equal to sin h z, and hence sin h z whole square is equal to I sin I z whole square, which is equal to sin I z whole square, that is sin h z modulus of sin h z whole square. This is equal to I sin I z whole square, which is equal to sin I z whole square. Modulus of sin I z whole square. That is, if z is equal to x plus iy, sin h z whole square is equal to sin I into x plus iy whole square modulus, which is equal to again modulus of sin minus y plus ix whole square, which is our equation number 6. Also by result in the previous chapter, that is modulus of sin a into x plus iy whole square, that is modulus of sin a into x plus iy whole square, which is equal to, which we can write as sin square ax plus sin h square ay. And hence in particular, we have modulus of sin x plus iy whole square equal to sin square x plus sin h square y, and thus modulus of sin minus y plus ix whole square is equal to sin square y plus sin h square x. Substituting this in the equation number 6 yields modulus of sin hz whole square, which is equal to sin h square x, here we have square, so it is sin h square x plus sin square y. Periodicity. In view of the periodicity of the trigonometric functions sin z and cos z, it follows from the relations 3 and 5 that sin hz and cos hz are periodic with period 2 pi I. Also from equation 3 and 5, it follows that sin hz is equal to 0 if and only if z is equal to n pi I. That is, sin hz is equal to 0 only when z is equal to what? N pi I, where this n varies from 0 plus or minus 1 plus or minus 2 etc. And cos hz is equal to 0 if and only if when z is equal to pi by 2 plus n pi. Here z is equal to pi by 2 plus n pi. Here also n varies from, here we have I, it varies from 0 plus or minus 1 plus or minus 2 etc. Next we have other hyperbolic functions. The hyperbolic tangent of z is defined by means of the equation tan hz is equal to sin hz by cos hz. Tan hz is equal to, we have sin hz by cos hz. Of course, we know tan is equal to sin by cos, and is analytic in every domain in which cos hz not equal to 0. The function cot hz, sec hz and also cosec hz are the reciprocals of tan hz, cos hz and sin hz respectively. Next we have differentiation formulas. We have seen that d by dz of sin hz is equal to cos hz. And d by dz of cos hz is equal to sin hz. Similarly, it can be seen that d by dz of tan hz is equal to, here we have d by dz of cos hz is equal to sin hz, d by dz of tan hz is equal to sec h square z, d by dz of cot hz, cot hz is equal to minus cosec h square z, and d by dz of sec hz is equal to we have d by dz of sec hz is equal to minus sec hz into what? Tan hz. And what remains? D by dz of cosecant hz. Which is equal to minus cosecant hz into cot hz. So, here we have discussed hyperbolic functions, and we have so many formulas for finding the derivatives of so many functions. See you next time. Till then, take care.